We now come to one of the great truisms of chemistry, and it's beautiful in its simplicity. Like dissolves like. That means that polar molecules dissolve polar molecules, and nonpolar molecules dissolve nonpolar molecules. A good example is ethanol. Ethanol is an alcohol, and it is the drinking alcohol we're most familiar with. And what makes an alcohol is an OH group off of a carbon. Right? Well, we have all the makings of hydrogen bonding. We've got hydrogen attached to a very electronegative species oxygen, and we've got a very electronegative species oxygen with a lone pair, a non-bonded pair, just waiting for attraction. So here is hydrogen bonding. Now ethanol can do it to itself, hydrogen bond to itself, or if you throw it in water, it is almost infinitely miscible, which means that it will dissolve in an infinite number of proportions. It is so good at mixing, in fact, that if you had 50 milliliters of water and you added 50 milliliters of ethanol, which we sometimes abbreviate with ETOH, you would get less than 100 milliliters total. The attraction is so tight. It's so tight between neighbors. Juxtapose that with oil and water. Oil and water are what we call immiscible. They don't mix. Well, you can shake them up and kinetically get them to stay together for a little while, but they will form an interface, because oil is an example of a nonpolar molecule. Nonpolar simply means that the overall dipole of the molecule is 0. How does this arise? Well, for example, oils are usually long chains of carbon and hydrogen. The carbon's bound to each other, and then the hydrogen's coming off the carbon, and it'll keep going. The difference in electronegativity, that is, the amount of pull the electron has for either one of those atoms in the bond, in the single covalent bond, is very small for carbon and hydrogen. So the individual bond dipoles is very small. And when you add them up, you find that the small bond dipoles balance. That is, they are symmetrically arranged in the molecule. So the dipole for the whole molecule is 0. Recall that a solute is the thing that's dissolved in a solvent to make a solution. Lots of S's. The solvent, water, if the solvent is water, the solution is called an aqueous solution. Aqueous, aqua, coming from the Latin. Water, which is very polar, large dipole moment for the whole molecule, dissolves almost anything with any degree of polarity, molecules as well as ionic compounds. Ionic compounds have full charge transfer of that electron, like the electrons are moving from the metals over to the non-metals. In molecules, remember I said it's a partial transfer, that little squiggly D plus. But either way, you have a positive end and a negative end in the compound. And like dissolves like because they have the same kind of forces in between neighbors. Because water is so good at dissolving so many things, it is often called the universal solvent. This is why you rarely find pure H2O. It takes extremely high temperatures to break the bonds, for example, in sodium chloride, table salt. But all you gotta do is throw it in your pasta water and instantly you have sodium ions and chlorine ions. When you have a substance, a liquid, that conducts electricity, we've got a special name for it. Okay, pure distilled water. Distilled means that you've evaporated it, so this is a way in order to purify it, so you just have H2O. It does not conduct electricity. When we put sugar in water, we also find it's non-conducting. This is called a non-electrolyte. That's the second example. But bang, when we put that sodium chloride into water, we conduct electricity. We have the light bulb is going off. This is because we have a solution filled with ions. And when you apply electrons in a external wire, electricity, it's going to be the species here that carry it to the other side of the bulk material. Right? So the electron is carried by the ions through the material. This is called an electrolyte. Water itself cannot conduct electricity. That's important for you to realize. It has no free ions. So why can't we watch TV underwater in our bathtubs? Because of all the lovely dissolved ions in that bath water. Here's a nice example. I like this picture. We've got chlorine is the negative, sodium's the positive. Okay, we've got cations and anions together, fit in this beautiful rigid lattice. Here comes the water. And you'll notice that the negative oxygen, that's my delta over here, is attracted to the opposite, I'm sorry, that's delta negative, is attracted to the opposite sign of the sodium. Over here, we've got chlorine, it's negative, it's attracted to the delta positive, the partial positive charge set up by the hydrogens. Okay? And each ion is totally surrounded, solvated by water molecules. This stops it from reforming. This is what you get in your pasta water. All right. Now molecules can also dissolve, obviously, but they do not have full charges. What we're looking at here is the molecule staying intact. For example, here is alcohol, right? And this is actually methanol, wood alcohol. So there's only one carbon, that's what the black guy is. All right, and here's my OH group. Here's a delta negative, here's a delta positive. Here come the hydrogens. The hydrogens are delta positive. The oxygen, this big old oxygen, he's delta negative. Delta positive, delta negative. There's an attraction between the opposite of signs. You'll notice that as this gets solvated or by solvent particles, water, it does not break into its individual atoms. The whole species stays together. But dissolved ions in water are very important. Our bodies need electrolytes to function. You've probably heard this on TV commercials that you need to replenish the electrolytes lost when you sweat. If you ever tasted your sweat, it tastes salty. Sodium and chloride are very common ions in our bodies, and they're needed because they carry electric current. And electric current is necessary for your personal body functions. The dissolved salts in the body are critical for maintaining blood pressure, nerve function, and healthy cells. In fact, if you drink pure water, H2O distilled, it's going to kill you. You need to keep bringing in electrolytes because your body naturally flushes them out. When the University of Florida Gators tried to figure out how to help their students from dropping in the sizzling Florida heat, they tried the usual dehydration remedy back in 1965, which was salt tablets. They did not help. Then they tried orange juice, but that caused stomach cramps. Finally, the team doctor, Dana Shires, who I believe just died last year, and the University of Florida medical researcher, Robert Cade, came up with a solution. They realized that salt tablets replace the salts lost by sweat, but not the water. Without water, these salt tablets just make dehydration worse. Orange juice caused stomach cramps because of the high sugar content, and the stomach kept in which the stomach kept water from passing through the stomach wall and into the cells where it was needed. So what they did is they figured out a concoction of sweat. Okay, check out sweat and Gatorade. Now the first Gatorade did have magnesium in about the same amounts, but they don't use it anymore, I believe, because of the way I have to put it in there. It makes it taste terrible. And they put in those sodium, potassium, and chloride ions. In order to make it palatable, because people got kind of tired of drinking something that tasted like sweat, they also put in sugar, but nowhere near the amount of sugar in orange juice. Okay. All right. Now, what happened then was the Gators went on to a 9-2 season in '66 and the Orange Bowl. Time after time, the papers would report that they outplayed their opponents, even under conditions that, I guess, I like this guy, Keith Jackson said, would make a salamander sweat. Now, Gatorade in the 21st century is not the same as it was in '65. Like I said, there's no more magnesium ions, and there's lots of wild flavors and colors. But you'll notice even in the hospital, they're very careful that intravenous saline solutions have enough sodium chloride, but not too much, because then cells will start to respond if there's too much discrepancy between the natural cell concentration and the liquid coming into the body. Today, we have nothing really that has gotten better for athletes than Gatorade, but we do have what are called fortified drinks, performance drinks, and they're adding vitamins, mostly sugar though. Please be careful when you're looking at these that you're not just paying a lot of money for sugar. I do not know the rules on what they can or cannot say about what's in their drinks. Sometimes you wonder if they just passed expensive drinks over the top of the mouth of the container. Remember this from chapter 1. This is what table salt looks like in its crystal form, and on the right what it looks like as the ions, and we've already seen that. Okay. The polar molecules stabilize the ions as they break apart. I showed you a smaller picture of that before. I like to call this ion soup, and here I've explicitly put in the pluses and minuses for the attraction of unlike charges. You got to understand though, it's a little bit perhaps confusing because like dissolve like does not I guess depends upon unlike charges attracting each other. So opposites attract, yes, but overall we have polar plus polar or nonpolar plus nonpolar suffices for like dissolves like. Okay, and this is the bottom way that we talk about the solvation of sodium chloride. He starts off as a solid, there's water as a liquid, and then for our products on the right we have sodium chloride in water, solvated by water, solvated by water. We can usually predict the nature of the ions present in a solution of an ionic compound from the chemical name of the substance. Many ions are polyatomic, with one of the elements being oxygen. We need to be familiar with them. Here's a list from your textbook, and I need you to memorize this. Right? You've got acetate, bicarbonate, carbonate, hydroxide, hypochlorite, that's the stuff in bleach, nitrates, nitrites. You'll notice it's got the same charge for the overall molecule, but one less oxygen. Phosphate, which has got a phosphorus and oxygen. Sulfate, which has got a sulfur and oxygen. Notice the sulfite, she's got 3 oxygens, same charge. And ammonium ion, that's the only one up there that is a cation. We can talk about generalizations with regard to solubilities in water of ionic compounds. Because water is such a wonderful solvent, it's important that we appreciate what can be in our water. Insoluble is defined by extremely low solubility. And all ionic compounds have at least a very small solubility in water. That's not what we're going to concern ourselves with. We're going to concern ourselves with black and white. And to that regard, we have a number of rules. You will not have to memorize this. I just need you to be able to use it. So all 1A metals, that's these guys. Sodium and potassium are the ones we're going to focus on, and ammonium compounds are soluble. All nitrates are soluble. All chlorides, well, except for very few, and I remember this as slim. Chances are slim that these will dissolve. Silver, lead, and mercury. But most chlorides are soluble. Most sulfides are soluble. Most carbonates are not soluble, except we have these exceptions from above. Right. And most sulfides are insoluble. How do we use this? Well, for example, if I have, let's look at the first one, which are cations. And so let's just pick an anion. Na, or we could have hydroxide, KOH, where, if you'll recall, that OH group, when we're talking about acids and bases, where OH is hydroxide. So these are molecules in a ionic form. So these are all soluble. Right? And in fact, if you look at a lot of your vitamins or household solutions, they will be sodium this and ammonium that. Because the manufacturer is trying to deliver the other ion. In the sodium case or the potassium case, they're trying to deliver the anion, and in the ammonium case, they're trying to deliver the anion 2. I'm sorry, the anion 2. So he will be plus, and then you'll see something like ammonium carbonate. And that's to make sure that you get the carbonate in solution. All right, other examples. I say most sulfates are soluble. So that means that calcium sulfate, and remember this guy's a plus 2, she's a minus 2. The way we figure out how to write these is to take the charges, the numbers themselves, and make them subscripts on the opposite ion. If they have the same subscript, the same number, we forego it, and I don't need then the parentheses. But he would be soluble. So if I put him in water, he would become a solution. Okay. It says most chlorides are soluble. Ca2 plus, chloride is minus, so you would need Ca1 and chloride sub 2. We don't usually write the 1, so this would be written like that. And again, if I added him to water, he would be soluble. We indicate that by the AQ, means he has formed a solution with water. Okay. Carbonate, Ca2 plus carbonate 2 minus. We write that as CaCO3 because they're both negative 2. We're going to have the same deal as in the sulfate. If I add him to water, will not dissolve. It is insoluble. No solution. Okay. All right. And sulfides. Calcium 2 plus, sulfur's 2 minus, just like oxygen underneath it. And CaS will stay a solid in water. It will not dissolve. It will not form a solution. How about covalent compounds in their solution? Sucrose. This is a disaccharide carbohydrate. This is a molecule. That's what makes something a molecule, is that it has covalent bonds. Well, water does not pull them apart into their individual ions. Instead, it surrounds it and is attracted to opposite charges. Okay, all right. Some things, of course, do not, or molecules do not dissolve in water. For example, diamonds. And that is simply because it is nonpolar. is definitely, though, covalent. This is graphite, and they're both all carbons. But it's fascinating. We're talking about how important the arrangement of the H2Os and the bent shape of water. Check out the difference in the macroscopic versus microscopic properties of graphite versus diamond. And it is simply the way these are bonded to each other, the structure, that gives them such different properties. Okay, now some molecules, this is the last thing we're going to talk about, some molecules have a polar end, and here we have an anion, and this is soap, okay? And then we have this very large part that is nonpolar. Do you remember me saying that carbon and hydrogen, the individual bond dipoles, are small, and overall the molecule, or the stretch, in case this is not a full molecule, so it's a partial molecule, the long linear chain of carbons is nonpolar. This is kind of neat because it does a twofer. The polar end dissolves in water, which is polar. We call it the solvent, right? Because it is the material that is in greater proportion. And then the nonpolar end and in this case it's a hydrocarbon chain. Remember, hydrogen and carbon makes up a hydrocarbon. Dissolves grease. And here it's hard to say who's the solvent and who's the solute. But the grease, which contains dirt on your hand, dissolves in the inside of this. Well, the molecules are sitting in here, and each time you have this is a different way to write these long chains. Every time you have a creek, you've got a carbon there. This is just an easier way to write this long molecule. Okay? So the grease dissolves the long nonpolar part here, and then the polar end dissolves in the surrounding water. So you collect the grease. The net effect is you collect the grease, which has the dirt, and then the water rinses the whole thing away. And that is how soap works. That is also how red wine works. Red wine also has a polar and nonpolar end in some of the molecules called tannins in them. And it will, the nonpolar end will dissolve the grease of red meat, the fat, or euphemistically called the marbling, that has accumulated on your tongue. And the saliva will dissolve the other end of the molecule, which is polar. So this whisks it away from your tongue, and they call this cleaning your palate. That's why they recommend you drink red wine with red meat. You don't want to drink red wine with white meat simply because the tannins of red wine have a lot of flavor, strong, and white meat is more delicately flavored than red because, well, one of the reasons because is it does not have all the marbling, the fat. So red meat and red wine go together beautifully.